Out here, in the deep stillness of space, things seem calm, but the cosmos is not always quiet. There are moments, brief, brilliant moments, when the universe releases unimaginable energy, explosions that can outshine galaxies. Moments when stars collapse, space quakes, and time seems to tremble. These are the most powerful explosions in the universe. In the vast darkness between stars, events unfold that defy human comprehension. Forces gather, energies build, and then, in an instant that might last only seconds or stretch across millennia, the fabric of reality itself is transformed. These cosmic cataclysms are not like explosions on Earth. They operate on scales so immense that our planet, our solar system, even our entire galaxy, becomes insignificant by comparison. Yet in their violence lies a profound beauty, a reminder that destruction and creation are two sides of the same cosmic coin. As we drift through the night sky together, we will witness the most extreme events known to science. From the death throes of massive stars to the collision of neutron stars dense enough to warp space itself. From ancient quasars blazing across billions of light years to the very beginning of time in the Big Bang. Each explosion tells a story of matter and energy, of gravity and light, of endings that become beginnings. These stories have been written in starlight, in cosmic rays, in gravitational waves rippling through the very fabric of space-time. Tonight, as stars twinkle gently above us, we begin a journey through the most violent events in all of existence. But we will approach them with wonder rather than fear, with awe rather than terror. Because in understanding these cosmic extremes, we gain perspective on our own place in this vast, dynamic universe. Close your eyes, breathe deeply, and prepare to witness the most magnificent fireworks display that nature has to offer. The silence before the storm is about to break. When we think of explosions, our minds often conjure images of bright flashes, billowing smoke, and thunderous sound. But space tells a different story. In the vacuum of the cosmos, explosions unfold in eerie silence, with no air to carry sound waves. Yet what these cosmic events lack in noise, they make up for in pure, unfiltered energy. An explosion in space is fundamentally a rapid release of energy. It might be electromagnetic energy in the form of light, from the gentle infrared to the deadly gamma rays. It might be kinetic energy, propelling matter outward at speeds approaching that of light itself. Or it might be gravitational energy, rippling through the very fabric of space-time like waves on a cosmic ocean. Without the resistance of air, these explosions spread differently than they would on Earth. There is no fireball in the traditional sense, no mushroom cloud rising skyward. Instead, energy and matter expand in perfect spheres, obeying only the laws of physics in their purest form. Radiation streams outward at the speed of light, while ejected matter continues its journey potentially, hardly slowing unless it encounters another object. The scale of cosmic explosions dwarfs anything we know on our small blue world. The most powerful nuclear weapon ever detonated on Earth, the Tsar bomber, to about 50 million tons of TNT. Yet even this pales in comparison to even modest stellar explosions, which can release energy equivalent to 100 billion trillion tons of TNT in a matter of seconds. One followed by 23 zeros, a number so large it escapes intuitive understanding. To better comprehend these scales, imagine our sun. Every second, our star tons of matter into pure energy through nuclear fusion. This powers all life on Earth, warms our oceans, drives our weather, and has done so reliably for billions of years. Now imagine a single explosion releasing more energy than our sun will produce in its entire 10 billion year lifetime. Such is the power of a supernova, and supernovae are just the beginning of our journey. In space, explosions also take many forms. Some are sudden and brief, like the collision of neutron stars, unleashing their fury in a flash lasting mere seconds. Others unfold over thousands or millions of years, like the slow expansion of supernova remnants. Some are visible across the entire electromagnetic spectrum, while others remain hidden except in certain wavelengths or through the subtle vibrations of gravity itself. Different physical processes drive these events. Nuclear explosions occur when the delicate balance of forces in a star fails, triggering runaway fusion or collapse. Gravitational explosions happen when massive objects merge, converting orbital energy into gravitational waves and heat. Electromagnetic explosions surge when magnetic fields twist and snap, releasing stored energy in sudden bursts. These cosmic cataclysms also vary in their composition. Some expel matter rich in heavy elements like gold and uranium. Others release their energy primarily as radiation, gamma rays or neutrinos. Some create new cosmic structures, neutron stars or black holes, objects so extreme they continue to influence their surroundings for billions of years. What unites all cosmic explosions is their role as agents of change. In the slow dance of cosmic evolution, explosions mark critical transitions. They scatter the seeds of new stars, distribute elements necessary for planets and life, and shape the structure of galaxies. Without these violent events, the universe would be a different place. Perhaps one where stars like our Sun and planets like Earth never had the opportunity to form. As we float here beneath the stars, consider that many of the elements in your body, the iron in your blood, the calcium in your bones, the carbon in your cells, were forged in ancient stellar explosions billions of years ago. We are, in a very real sense, children of cosmic catastrophe, our existence made possible by the most extreme events in the universe. The energy scales of cosmic explosions can be difficult to grasp through numbers alone. Instead, let us consider their effects. A single gamma ray burst directed at Earth from even thousands of light years away could potentially strip away our protective atmosphere. The collision of two neutron stars creates conditions so extreme that gold and platinum form in abundance, seeding the cosmos with precious metals. The expansion of the universe itself, sometimes described as the echo of the Big Bang, continues to carry galaxies away from each other billions of years after the initial event. Timescales, too, differ dramatically from terrestrial explosions. On Earth, an explosion might last mere fractions of a second. In space, while the triggering event might be similarly brief, the effects propagate for unimaginable durations. The light from a supernova that occurred during the time of the dinosaurs might only now be reaching our telescopes. The debris from an explosion that happened when our solar system was young might still be traveling through space, perhaps to one day seed the formation of new stars and worlds. Scientists classify cosmic explosions based on their energy output, duration, and mechanism. A supernova might release 10 to the power of 44 joules of energy. A hypernova, even more energetic, can approach 10 to the power of 46 joules. Gamma ray bursts, the most luminous electromagnetic events known, can release energy equivalent to the rest mass energy of our Sun in mere seconds. Even the collision of two black holes, invisible in traditional light, can convert several solar masses worth of matter into pure gravitational wave energy. These explosions leave behind distinct signatures. Supernovae create beautiful, expanding shells of gas and dust, visible for thousands of years. Neutron star mergers scatter heavy elements across space, while potentially forming a new black hole at their center. Gamma ray bursts punch powerful jets through space that can be detected across billions of light years. Each signature tells astronomers about the nature and circumstances of the original event. Observing these cosmic fireworks has become increasingly sophisticated. No longer limited to visible light, modern astronomers use instruments sensitive to radio waves, infrared, ultraviolet, X-rays and gamma rays. The newest frontier is multi-messenger astronomy, combining electromagnetic observations with gravitational waves, cosmic rays, and neutrinos to build a comprehensive picture of these extreme events. What makes cosmic explosions particularly fascinating is that despite their destructive power, they are essential for creation. The elements forged in supernovae become the building blocks for new stars, planets, and eventually, life. The shock waves from explosions compress nearby clouds of gas and dust, triggering the birth of stars. Even the dramatic collision of galaxies, with their supermassive black holes and billions of stars, ultimately leads to the formation of new, larger galaxies with fresh cycles of stellar birth and death. In the grand cosmic perspective, explosions are not aberrations or accidents. They are integral parts of the universe's metabolism, the way it recycles matter and energy, the way it evolves from simplicity to complexity, from the primordial explosion of the Big Bang to the silent detonations occurring even now in distant galaxies. Explosions write the narrative of cosmic history. As we continue our journey through the most powerful explosions in the universe, remember that what we are witnessing is not mere destruction. It is transformation on the grandest scale, the universe remaking itself again and again across the vast expanse of time. Each flash of brilliance in the cosmos marks not an ending, but a transition, a moment when the familiar gives way to something new. Unlike anything we know on Earth, cosmic explosions are not loud, but they are vast, and they echo for eons. To understand the most powerful explosions in the universe, we must first understand stars. These cosmic furnaces are where our story truly begins, for it is in their lives, and especially in their deaths, that the universe produces its most spectacular displays of power. Stars are born in nebulae, vast clouds of gas and dust that float in the darkness between existing stars. Within these cosmic nurseries, gravity gradually pulls matter together. As more and more hydrogen gathers in one place, pressure and temperature rise. The cloud contracts, spins, and heats. Eventually, at the center of this gathering storm, when temperatures reach about 10 million degrees Celsius, something miraculous happens. Hydrogen atoms, squeezed together with incredible force, begin to fuse into helium. Nuclear fusion ignites and a star is born. Our own sun is such a star, a colossal fusion reactor that converts about 600 million tons of hydrogen into helium every second. The energy released in this process travels outward from the core, eventually reaching the surface and radiating into space as heat and light. This delicate balance between the inward pull of gravity and the outward push of fusion energy maintains the stability of the star for billions of years. But stars do not all live the same lives or meet the same fates. Their destinies are written in their mass, determined at the moment of their birth. More massive stars burn brighter and hotter, consuming their fuel at a ferocious rate. Our Sun, a relatively average star, will shine steadily for about 10 billion years. A star 10 times more massive might exhaust its fuel in just 10 million years, a cosmic blink of an eye. Meanwhile, a small, red dwarf star with half the mass of our Sun might smolder gently for more than 1 trillion years. As a star ages, its core gradually fills with helium, the ash of hydrogen fusion. Eventually, for stars like our Sun and larger, the core becomes predominantly helium, while hydrogen fusion continues in a shell around this core. This causes the star to expand and cool at its surface, transforming into a red giant. For stars similar in mass to our Sun, this expansion will eventually engulf the inner planets. In about 5 billion years, our own star will expand to consume Mercury, Venus, and possibly Earth. What happens next depends crucially on the star's mass. For stars like our Sun, the helium core will eventually become hot and dense enough to ignite in a helium flash, fusing helium into carbon and oxygen. After this phase, the star will shed its outer layers in beautiful, expanding shells of gas called planetary nebulae. The exposed core, now a white dwarf, will cool slowly over billions of years until it fades to a black dwarf, a cold remnant of its former glory. But for stars more than 8 times the mass of our Sun, a far more dramatic fate awaits. These stellar giants progress through a sequence of fusion reactions, forming elements of increasing atomic weight. Helium fuses into carbon and oxygen. Carbon fuses into neon and magnesium. Neon becomes silicon. Silicon transforms into iron. Each stage burns faster than the last, as the star desperately tries to maintain equilibrium against the inexorable pull of gravity. This progression reaches a critical point with iron. Unlike lighter elements, the fusion of iron does not release energy but consumes it. Iron accumulates in the core like poison, a fusion dead end. When enough iron builds up, nuclear fusion can no longer generate the energy needed to resist gravity. What happens next occurs with breathtaking speed. In less than a second, the iron core collapses. Electrons are forced into protons, forming neutrons and releasing ghostly particles called neutrinos. The core shrinks from the size of the Earth to a sphere just 20 kilometers across. The outer layers of the star, suddenly unsupported, fall inward at about 25% the speed of light. When they hit the newly formed neutron core, they bounce, creating a shockwave that propagates outward. This is the birth of a supernova, one of the most energetic explosions in the universe. For a brief period, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The energy released in this explosion is so vast that it forges elements heavier than iron, gold, silver, uranium, and many others, in quantities that dwarf what human civilization has ever mined from Earth. The violence of this process is difficult to comprehend. Temperatures reach billions of degrees. The shockwave expands at thousands of kilometers per second. The dying star, which took millions of years to evolve, is torn apart in minutes. Matter that once constituted the star is hurled into space, forming an expanding shell that will continue to grow for thousands of years, eventually merging with the interstellar medium. Not all of the star is expelled, however. For stars between 8 and about 20 times the mass of our Sun, the core remains as a neutron star, a city-sized object so dense that a teaspoonful would weigh billions of tons on Earth. These objects spin rapidly, sometimes hundreds of times per second, emitting beams of radiation from their magnetic poles that sweep through space like cosmic lighthouses. For stars with more than about 20 times the mass of our Sun, even the pressure of neutrons cannot halt the collapse. The core continues to shrink beyond the neutron star stage, becoming so dense that it forms a black hole, an object whose gravity is so intense that not even light can escape. The birth of a black hole is one of the most extreme events in the universe, a moment when the laws of physics as we understand them begin to break down. The explosions that mark these stellar deaths serve a vital purpose in cosmic evolution. They scatter newly forged elements into space, enriching the interstellar medium with the building blocks needed for new generations of stars and planets. Without supernovae, the universe would consist almost entirely of hydrogen and helium. There would be no rocky planets, no complex chemistry, and no possibility for life as we know it. Consider that every atom of calcium in your bones, every atom of oxygen you breathe, every atom of carbon in your DNA was created inside a star and likely scattered by a supernova explosion billions of years ago. As astronomer Carl Sagan famously said, "We are made of star stuff." More precisely, we are made of star stuff that was violently expelled in cosmic explosions of unimaginable power. The study of stellar evolution and death has been revolutionized by modern astronomy. We can now observe supernovae in distant galaxies, study the remnants of ancient explosions in our own galaxy, and even detect the neutrinos and gravitational waves produced during stellar collapse. Each observation adds to our understanding of these cosmic cycles of creation and destruction. There is a profound beauty in this stellar life cycle, a poetry in the knowledge that stars must die so that new worlds might live. The most massive stars, those that live the most dramatic lives and die the most violent deaths, contribute the most to enriching the cosmos. In their sacrifice is the promise of new beginnings, of worlds yet unformed, of possibilities not yet realized. As we gaze at the night sky, the stars might seem eternal and unchanging, but they are dynamic, evolving systems caught in the great cosmic dance of gravity and nuclear forces. Some of the stars we see tonight are already dead, their light still traveling across the vast distances of space to reach our eyes. Others are in their prime, steadily fusing hydrogen into helium as our Sun does. Still others might be approaching their end, soon to flare into brilliance before fading away. When a star can burn no longer, it dies in brilliance, scattering itself across the void. Among all the explosive phenomena that grace our universe, few rival the sheer magnificence of supernovae. These stellar detonations represent the most dramatic endings in the cosmic story of stellar evolution, moments when stars bid farewell to existence in displays of light and energy that can outshine entire galaxies. A supernova is, in essence, the death explosion of a star. But this simple definition belies the extraordinary complexity and diversity of these events. Like snowflakes or human fingerprints, each supernova has its unique characteristics, shaped by the star that gives rise to it and the circumstances of its demise. Yet patterns emerge in this diversity, allowing astronomers to classify these explosions and understand their underlying mechanisms. Two primary types of supernovae dominate our cosmic landscape, each with its distinct origin story and signature. Type Ia supernovae occur in binary star systems where at least one star is a white dwarf, the dense, Earth-sized remnant of a star similar in mass to our Sun. These white dwarfs are stable unless disturbed by a companion star. When a white dwarf pulls matter from its companion or merges with another white dwarf, it can reach a critical mass, triggering a runaway fusion reaction that tears the star apart in seconds. Like cosmic timekeepers, Type Ia supernovae explode with remarkably consistent brightness, making them invaluable as standard candles for measuring cosmic distances. Type II supernovae, by contrast, represent the explosive deaths of massive stars, typically those more than 8 times the mass of our Sun. As we explored in our previous chapter, these stellar giants progress through a series of fusion reactions until they develop ion cores. Unlike lighter elements, ion fusion consumes rather than releases energy. This fusion dead end leads to catastrophic core collapse, followed by a spectacular rebound explosion. The details of this process remain an active area of research, with sophisticated computer simulations helping astronomers understand exactly how the shockwave propagates through the dying star. The brightness of a supernova explosion defies easy comprehension. At its peak, a typical supernova might shine with the luminosity of 10 billion suns. For a brief period lasting days or weeks, a single dying star can outshine all the other stars in its galaxy combined. If a star 20 light-years from Earth were to go supernova, it would appear brighter than the full moon in our sky, visible even during daylight hours. Thankfully, no stars currently capable of going supernova exist within this potentially hazardous distance from our solar system. This extraordinary brightness makes supernovae visible across vast cosmic distances. Modern astronomical surveys routinely detect supernova in galaxies billions of light-years away, providing glimpses of stars that died when the universe was young. Each of these distant flashes represents not just the end of a star, but a window into cosmic history, allowing astronomers to study how star formation and death have evolved over the universe's lifetime. The energy of a supernova explosion manifests in multiple forms. About 99% of the energy is carried away by neutrinos, ghostly particles that interact so weakly with matter that trillions pass through your body every second without effect. The remaining energy divides between the kinetic energy of the expanding debris and electromagnetic radiation across all wavelengths, from radio to gamma rays. This energy output occurs over different timescales, with the neutrino burst lasting mere seconds, the initial brightness peaking over days or weeks, and the expansion of the debris continuing for thousands of years. Throughout human history, several supernovae have been bright enough to be seen with the naked eye from Earth. Perhaps the most famous occurred in the year 1054 CE, recorded by Chinese, Japanese, Arab, and possibly Native American observers. The remnant of this explosion is now known as the Crab Nebula, a still expanding cloud of gas and dust that harbors at its center a rapidly spinning neutron star, the dense corpse of the original star. When astronomers point their telescopes at the Crab Nebula today, they witness the nearly 1,000-year-old aftermath of a stellar cataclysm, a structure still energized by the power of the original explosion. A more recent naked-eye supernova appeared in 1987, designated SN 1987A. Located in the Large Magellanic Cloud, a satellite galaxy of our Milky Way, this supernova provided astronomers with an unprecedented opportunity to study such an event with modern instruments. For the first time, neutrinos from a supernova were detected, arriving at Earth a few hours before the visible light, confirming theoretical predictions about core collapse. Observations of SN 1987A continue to this day, as astronomers track the expanding shockwave and the formation of dust in the cooling debris. The material ejected during a supernova explosion enriches the surrounding interstellar medium with heavy elements. Carbon, oxygen, silicon, and iron, forged during the star's life, scatter into space, along with even heavier elements created during the explosion itself through a process called rapid neutron capture, or the R process. This cosmic alchemy produces elements like gold, platinum, and uranium, seeding the galaxy with the building blocks for future generations of stars and planets. When supernova debris eventually mixes with nearby gas clouds, it can trigger the formation of new stars, continuing the cosmic cycle. Some of these new stars will incorporate the heavy elements from the supernova, forming with planets already endowed with the complex chemistry necessary for life. Our own solar system, likely formed in a region enriched by multiple previous supernovae, explaining the abundance of heavy elements on Earth and in our bodies. The expanding shells of gas and dust left behind after a supernova are called supernova remnants. These structures evolve over thousands of years, gradually merging with the interstellar medium. During their expansion, they create beautiful, intricate formations visible to our telescopes. The Crab Nebula shows delicate filaments of superhot gas, while the Vela supernova remnant resembles wispy veils of colorful mist stretching across several light-years. The Cygnus Loop, also known as the Veil Nebula, displays ribbon-like structures where the expanding shockwave interacts with the surrounding interstellar medium. These remnants continue to influence their surroundings long after the initial explosion. They compress nearby gas clouds, potentially triggering star formation. They seed the interstellar medium with magnetic fields and cosmic rays, high-energy particles that travel through space at nearly the speed of light. They create bubbles of hot, diffuse gas that can span hundreds of light-years, sculpting the structure of the galaxy itself. Astronomers have identified hundreds of supernova remnants in our Milky Way galaxy, each at a different stage of evolution. Some, like Cassiopeia A, are young, having exploded only about 300 years ago. Others, like the Veil Nebula, are middle-aged, roughly 10,000 years old. The oldest identifiable remnants might be hundreds of thousands of years old, their expanded shells now diffuse and difficult to distinguish from the background interstellar medium. The study of supernovae and their remnants has been revolutionized by multi-wavelength astronomy. What appears as a faint wisp in visible light might glow brightly in X-rays or radio waves. By combining observations across the electromagnetic spectrum, astronomers build comprehensive pictures of these complex structures and the processes that drive their evolution. Space-based observatories like the Hubble Space Telescope, the Chandra X-ray Observatory, and the James Webb Space Telescope provide unprecedented views of these cosmic explosions and their aftermath. Supernovae also serve as cosmic laboratories for extreme physics. The conditions during a supernova explosion cannot be replicated in terrestrial laboratories, with temperatures reaching billions of degrees and densities exceeding those of atomic nuclei. By studying these explosions, physicists gain insights into the behavior of matter under the most extreme conditions imaginable, testing the limits of our understanding of fundamental physical laws. The classifications of supernovae extend beyond the basic Type Ia and Type II categories. Astronomers recognize subtypes based on the presence or absence of specific elements in their spectra and the shape of their light curves, how their brightness changes over time. Type Ib and Ic supernovae, for instance, result from massive stars that have lost their outer hydrogen layers before exploding, either through stellar winds or interaction with companion stars. These nuances in classification reflect the diverse evolutionary pathways that lead stars to their explosive endings. Some supernovae leave behind what astronomers call a compact remnant, either a neutron star or a black hole. These exotic objects represent the condensed cores of the original stars, compressed by gravity to densities that defy intuition. A neutron star typically has a mass greater than our Sun, compressed into a sphere about 20 kilometers in diameter. The density of neutron star material is so extreme that a teaspoonful would weigh billions of tons on Earth. Black holes are even more extreme, their mass concentrated so densely that not even light can escape their gravitational pull. The frequency of supernovae provides a measure of star formation and death throughout cosmic history. In a typical galaxy like our Milky Way, astronomers estimate that a supernova occurs about once or twice per century. Across the observable universe, a supernova explodes approximately every second, each marking the violent end of a stellar life and the potential beginning of new cosmic structures. Despite their importance and prevalence, much about supernovae remains mysterious. The exact mechanism by which the shock wave in a core-collapse supernova propagates through the star is still debated. The precise origins of some supernova subtypes remain uncertain. The details of element formation during these explosions continue to be refined through observation and simulation. Each new supernova detection provides additional data to help resolve these questions. For civilizations throughout history, the appearance of a bright supernova in the sky often inspired awe, fear, or religious interpretation. Chinese astronomers described the supernova of 1054 CE as a guest star, a temporary visitor to an otherwise unchanging celestial realm. Medieval European records of the supernova of 1006 CE the brightest ever recorded, describe an extraordinarily brilliant star that casts shadows at night. Today, we understand these events not as omens or supernatural occurrences, but as natural stages in the life cycle of stars, no less wondrous for being explicable by science. The search for supernovae has been transformed by automated sky surveys that scan large portions of the night sky repeatedly, comparing images to detect changes that might indicate a new explosion. Projects like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory are expected to discover hundreds of thousands of new supernovae, providing unprecedented statistical samples to refine our understanding of these cosmic explosions. As we contemplate the vast energy and transformative power of supernova, it becomes clear that these stellar deaths are not merely destructive events, but regenerative processes essential to the cosmic cycle. A single supernova can breathe life into a galaxy, seeding worlds with the elements of existence. If supernovae represent the standard explosive death of stars, then hypernovae are their more dramatic, more energetic cousins. These rare and exceptionally powerful stellar explosions push the boundaries of cosmic violence, releasing energy that dwarfs even the mighty supernova. As we journey deeper into the realm of cosmic explosions, we find that nature continues to surprise us with ever more extreme events. A hypernova, sometimes called a superluminous supernova, outshines a typical supernova by factors of 10 to 100. While a standard supernova might reach a peak luminosity equivalent to 10 billion suns, a hypernova can briefly shine with the light of 1 trillion suns. This extraordinary brightness allows astronomers to detect them across vast cosmic distances, providing glimpses of stellar explosions that occurred when the universe was young. What creates these cosmic overachievers? The answer lies in exceptionally massive stars, typically more than 40 times the mass of our Sun. These stellar titans are rare in the modern universe, but were more common in the early cosmos when stars formed from pristine gas unmarked by previous generations of stellar explosions. When such massive stars reach the end of their lives, they do not go quietly. Unlike typical supernovae, the collapse of a hypernova progenitor creates conditions for more extreme energy release. The exact mechanisms remain areas of active research, but several factors contribute to their exceptional power. First, the sheer mass of the collapsing star provides more gravitational energy to convert into the explosion. Second, many hypernovae involve rapidly rotating stars, adding rotational energy to the mix. Third, the most powerful hypernovae appear linked to the formation of nascent black holes that power relativistic jets of material punching through the dying star. This connection between hypernovae and black hole formation reveals a fascinating overlap with another extreme cosmic phenomenon: gamma-ray bursts. Many long-duration gamma-ray bursts, which we will explore in more detail in our next chapter, appear to be powered by the same engine that drives hypernovae. In these cases, while the hypernova explosion expands in all directions, the gamma-ray burst represents a focused beam of energy along the rotation axis of the collapsing star, a cosmic spotlight of incredible intensity. The rarity of hypernovae makes them challenging to study. In a typical galaxy like our Milky Way, a hypernova might occur only once every few thousand years, compared to a supernova rate of 1 or 2 per century. This scarcity means that astronomers must survey vast numbers of galaxies to catch these events in action. Fortunately, their extreme brightness makes them visible across billions of light years, and automated sky surveys now regularly detect these cosmic explosions. One well-studied example is SN 2006-GI, discovered in 2006 and located in a galaxy some 4 billion light-years from Earth. This hypernova reached a peak brightness about 100 times greater than a typical supernova and faded much more slowly, remaining visible to telescopes for months. The energy released in this explosion exceeded anything astronomers had previously documented from a stellar death. The star that produced this cataclysm likely had a mass more than 100 times that of our Sun, placing it among the most massive stars known to exist. The chemical composition revealed in hypernova explosions offers clues to their progenitor stars and explosion mechanisms. Spectroscopic analysis, which breaks down light into its component wavelengths, shows signatures of elements like carbon, oxygen, and silicon moving at velocities approaching 10% of the speed of light. Some hypernovae show unusual abundances of heavy elements, suggesting exotic nuclear processes occurring during the explosion. Others reveal minimal hydrogen, indicating that the progenitor star had already shed its outer layers before exploding. The environments where hypernovae occur provide additional context for understanding these events. Many hypernova host galaxies show signs of active star formation and relatively low abundances of heavy elements. These conditions favor the formation of very massive stars that can end their lives as hypernovae. Some hypernovae, however, appear in seemingly quiet galactic neighborhoods, suggesting that stellar mergers or other rare evolutionary pathways might sometimes create the conditions for these extreme explosions, even in environments less conducive to forming single, very massive stars. The aftermath of a hypernova resembles that of a supernova, but scaled up in energy and extent. The expanding shell of debris carries more kinetic energy, potentially influencing the surrounding interstellar medium over greater distances. The production of heavy elements through rapid neutron capture processes might be enhanced, contributing more significantly to cosmic chemical enrichment. The compact remnant left behind, typically a black hole, might be more massive than those produced by standard supernovae, influencing the population of black holes throughout the universe. Hypernovae also serve as laboratories for testing theories about the most extreme forms of matter and energy. The conditions in these explosions approach those that existed in the very early universe, milliseconds after the Big Bang. By studying these natural cosmic accelerators, physicists gain insights into fundamental forces and particles that would be impossible to recreate in terrestrial laboratories. Each hypernova observation provides data points against which theoretical models can be tested and refined. The detection of hypernovae across cosmic history allows astronomers to track how these events have evolved over time. Evidence suggests that hypernovae were more common in the early universe when stars formed from primordial gas untouched by stellar nucleosynthesis. These early hypernovae likely played a crucial role in seeding the young universe with the first heavy elements, setting the stage for the formation of more complex structures, including, eventually, planets and life. Despite their power, detecting ancient hypernovae presents challenges. The light from explosions that occurred billions of years ago must traverse vast cosmic distances, during which it is stretched by the expansion of the universe, a phenomenon known as redshift. Advanced telescopes and sophisticated analysis techniques allow astronomers to identify these distant explosions and extract meaningful data from their faint signals. Future observatories promise to push these observations even further, potentially capturing hypernovae from the universe's first generations of stars. The distinction between the most powerful supernovae and the least energetic hypernovae is not always clear-cut. Rather than discrete categories, these explosions exist on a continuum of stellar deaths, with overlapping properties and energy ranges. This complexity reflects the diversity of massive stars and their evolutionary pathways, a reminder that nature rarely conforms to the neat classifications humans prefer to impose. When we observe a hypernova from Earth, we are seeing the end of a cosmic giant, a star so massive and short-lived that its entire existence might have lasted only a few million years. These stellar behemoths live fast and die young, their brief lives ending in explosions of almost incomprehensible violence. Yet in this violence lies creation, as the elements forged in these stars and scattered by their explosions become the building blocks for new cosmic structures. The study of hypernovae connects to broader questions about stellar evolution, black hole formation, and the chemical enrichment of galaxies. By understanding these rare but influential events, astronomers gain insights into how the universe has evolved from primarily hydrogen and helium to the chemically complex cosmos we inhabit today. Each hypernova represents a transformative moment in cosmic history, when a massive star's death becomes the potential birthplace of new stellar and planetary systems. As our observational capabilities continue to improve, we will undoubtedly discover hypernovae with even more extreme properties, pushing the boundaries of what we thought possible. The universe consistently reveals itself to be more dramatic, more energetic, and more varied than our theories initially predict. Each new discovery invites us to expand our understanding and appreciate the extraordinary processes that shape our cosmic home. Hypernovae are the universe's brightest screams, brief, dazzling, and deadly. In the vast darkness of space, there exists a phenomenon so energetic, so fleeting, and so mysterious that for decades it confounded our understanding of the cosmos. These events, known as gamma-ray bursts, or GRBs, represent the most luminous electromagnetic explosions known to occur in the universe since the Big Bang itself. They appear without warning, shine with unimaginable brilliance for mere seconds or minutes, and then fade away, leaving astronomers to piece together their origins from the afterglow they leave behind. The story of gamma-ray bursts begins not with astronomy, but with Cold War politics. In the 1960s, the United States launched a series of satellites called Vela, designed to monitor the Soviet Union for violations of the Nuclear Test Ban Treaty. These satellites carried detectors sensitive to the gamma rays that would be produced by nuclear detonations. In July 1967, two of these satellites detected something unexpected, a brief flash of gamma rays that did not match the signature of a nuclear test. Over the following years, more of these mysterious flashes were detected, always brief, always from different directions in the sky, and always puzzling. When this discovery was declassified and published in 1973, astronomers were presented with a genuine cosmic mystery. What could produce such intense bursts of the highest energy form of electromagnetic radiation? Early theories ranged from nearby flaring stars to comet collisions in our solar system. The debate over their origin continued for decades, with a fundamental question remaining unanswered. Were these explosions occurring within our galaxy, or at much greater cosmological distances? The breakthrough came in 1997 with the launch of the Bepo-SAX satellite, which could quickly determine the position of a gamma-ray burst with sufficient accuracy for optical telescopes to search for an afterglow. When GRB 970228 was detected, astronomers found a fading optical counterpart in a distant galaxy, proving that at least some gamma-ray bursts originated far beyond our Milky Way. The incredible brightness implied by this cosmic distance confirmed that gamma-ray bursts are among the most energetic phenomena in the universe. We now understand that gamma-ray bursts come in two primary varieties, short and long, divided roughly at the 2-second mark. While this might seem like an arbitrary distinction, it reflects fundamentally different cosmic processes. Long gamma-ray bursts, lasting more than 2 seconds, are associated with the deaths of extremely massive, rapidly rotating stars. As we discussed in our exploration of hypernovae, when such a star collapses, it can form a black hole that powers jets of relativistic particles along its rotation axis. These jets punch through the outer layers of the dying star and produce the gamma-ray burst. Short gamma-ray bursts, typically lasting less than 2 seconds, have a different origin story. These arise from the merging of two neutron stars, or possibly a neutron star and a black hole. As these incredibly dense objects spiral together, they generate powerful gravitational waves. When they finally merge, they create a cataclysm that launches jets of high-energy particles and radiation, resulting in a brief but intense flash of gamma rays. We will explore these mergers in more detail in a later chapter. The energy released in a gamma-ray burst staggers the imagination. During its brief existence, a GRB can release more energy than our Sun will produce in its entire 10 billion-year lifetime. If we convert this to an equivalent amount of TNT, we would need a 1 followed by 44 zeros tons of the explosive. Numbers this large lose meaning, so consider this: a single gamma-ray burst can briefly outshine the combined light of every star in the observable universe. This extraordinary energy output becomes slightly less mysterious when we understand the beamed nature of gamma-ray bursts. Rather than radiating energy in all directions equally, GRBs focus their emission into narrow jets, like cosmic spotlights. This beaming effect means that we only detect the small fraction of bursts that happen to have their jets pointed towards Earth. For every burst we see, there might be hundreds occurring with their jets oriented in other directions. This beaming also explains the extreme brightness, as all the energy is concentrated into a narrow cone rather than spread across the sky. The relativistic nature of these jets adds another layer of fascination. Material in a gamma ray burst jet travels at more than 99.9% the speed of light. At such velocities, the effects of Einstein's special relativity become pronounced. Time dilation, length contraction, and relativistic beaming all come into play, making gamma-ray bursts natural laboratories for testing physics under extreme conditions. The shockwaves produced when these jets interact with surrounding material accelerate particles to energies far beyond what our most powerful terrestrial accelerators can achieve. When a gamma-ray burst occurs, the initial flash of gamma rays is just the beginning. As the relativistic jet interacts with surrounding material, it produces an afterglow that can be detected across the electromagnetic spectrum, from radio waves to X-rays. This afterglow can persist for days, weeks, or even months, gradually fading as the shockwave expands and cools. By studying this afterglow at different wavelengths, astronomers can determine the burst's distance, energy, and environmental conditions, piecing together the story of its origin and evolution. The distances of gamma-ray bursts reveal another aspect of their significance. Most detected bursts originated billions of light-years away, meaning the light we observe began its journey when the universe was much younger. The most distant confirmed gamma-ray burst, GRB 130427a, occurred about 13 billion years ago, when the universe was less than 4% of its current age. By studying these ancient explosions, astronomers gain insights into the conditions of the early universe and the formation of its first generations of stars. Given their extreme brightness, it is natural to wonder about the effects a nearby gamma-ray burst might have on Earth. If a long GRB occurred within our galaxy and had one of its jets pointed directly at our solar system, the consequences could be severe. The intense radiation could damage Earth's ozone layer, exposing the surface to harmful ultraviolet radiation from the sun. The resulting increase in mutations and potential ecosystem disruptions might trigger a mass extinction event. Some scientists have speculated that past extinction events might be linked to nearby gamma-ray bursts, though evidence for this remains inconclusive. Fortunately, gamma-ray bursts are rare, especially in galaxies like our Milky Way. The conditions that produce long GRBs, very massive stars with rapid rotation and low metallicity, are more common in small, irregular galaxies than in large spirals like our own. Additionally, the highly beamed nature of GRBs means that even if one occurred in our galaxy, the probability of a jet pointing directly at Earth would be extremely low. Astronomers estimate that a dangerously close gamma-ray burst might occur once every few hundred million years, making it a very low probability threat to life on Earth. One particularly impressive gamma-ray burst, GRB 080319b, gained the nickname the Naked Eye GRB because it briefly reached a magnitude of 5.8, theoretically visible to the unaided human eye, despite originating about 7.5 billion light-years away. For a few moments, a single exploding star across more than half the observable universe was faintly visible to human eyes, a testament to the almost incomprehensible energy of these events. The detection and study of gamma-ray bursts involve a global network of satellites and ground-based observatories working in concert. When a space-based detector like NASA's Swift or Fermi satellites identifies a burst, it quickly determines its position and relays this information to observatories worldwide. Robotic telescopes automatically slew to the burst location, often beginning observations within seconds of receiving the alert. This rapid response system allows astronomers to capture the early afterglow, which contains crucial information about the burst's origin and environment. Beyond their astrophysical significance, gamma-ray bursts serve as cosmic beacons that allow astronomers to probe the intervening space between the burst and Earth. As the burst's light travels through distant galaxies and the intergalactic medium, certain wavelengths are absorbed by gas and dust along the way. By analyzing these absorption features, astronomers can determine the composition, temperature, and density of material in the early universe that would otherwise be invisible to our telescopes. In this way, gamma-ray bursts act as cosmic flashlights, illuminating the otherwise dark corridors of space. The environments where gamma-ray bursts occur provide additional clues to their nature. Long GRBs typically originate in regions of active star formation, consistent with their association with the deaths of young massive stars. Many long GRB host galaxies show relatively low abundances of heavy elements, supporting the theory that low metallicity helps massive stars retain the rapid rotation necessary to produce jets when they collapse. Short GRBs, by contrast, often occur in regions with older stellar populations, consistent with the longer time needed for binary neutron star systems to spiral together and merge. The connection between long gamma-ray bursts and certain types of supernovae has been confirmed through simultaneous observations. In several cases, astronomers have detected a supernova brightening in the days and weeks following a gamma-ray burst at the same location. These accompanying supernova belong to a specific subclass, type IC, with broad spectral lines, indicating a massive star that lost its outer hydrogen and helium layers before exploding. This association strengthens the collapsar model, which proposes that long GRBs result from the collapse of rapidly rotating massive stars that form jets along their rotation axes. The field of gamma-ray burst research continues to evolve as new observations challenge and refine existing theories. Unusual bursts that don't fit neatly into the short or long categories hint at additional physical processes or progenitor systems. Ultra-long gamma-ray bursts, lasting for hours instead of minutes, might result from the collapse of extraordinarily massive stars or events like the tidal disruption of stars by supermassive black holes. Each new discovery pushes astronomers to expand their theoretical frameworks and develop more comprehensive models of these extreme events. The detection of gravitational waves from the merger of two neutron stars in 2017, accompanied by a short gamma-ray burst and a kilonova optical counterpart, marked a new era in multi-messenger astronomy. For the first time, astronomers observed the same cosmic event through both gravitational waves and electromagnetic radiation, confirming the connection between neutron star mergers and short gamma-ray bursts. This landmark discovery opened new avenues for studying these cataclysmic events, combining complementary information from different messengers to build a more complete understanding of their physics. As we reflect on these beams from the void, we confront the dual nature of gamma-ray bursts. They represent both destruction and creation, the violent end of one cosmic story and the beginning of another. The elements forged and dispersed in these explosions become the building blocks for new stars, planets, and potentially life. The same jets that could theoretically threaten life on Earth if pointed our way have, over cosmic history, contributed to the conditions that made life possible in the first place. The study of gamma-ray bursts connects us to the most extreme environments in the cosmos and to the earliest epochs of cosmic history. Each burst provides a brief glimpse of the universe at its most energetic, a fleeting moment when the fabric of space is illuminated by the death throes of stars or the mergers of stellar remnants. In that moment, when a distant part of the cosmos briefly outshines all else, we are reminded of the dynamic, ever-changing nature of our universe. For a few fleeting seconds, the universe blinks with a light so bright and then returns to darkness. As we continue our journey through the most powerful explosions in the universe, we encounter a class of objects that seem quiet by comparison to supernovae or gamma-ray bursts, yet harbor the potential for sudden, catastrophic energy release. These objects, known as magnetars, represent perhaps the most extreme stellar remnants in the cosmos, combining incredible density with magnetic fields of almost incomprehensible strength. A magnetar is a type of neutron star, the collapsed core of a massive star that has exploded as a supernova. But while all neutron stars are extraordinary, magnetars stand apart due to their magnetic fields. A typical neutron star might have a magnetic field 1 trillion times stronger than Earth's. A magnetar, however, possesses a field 1,000 times stronger still, reaching levels of 10 to the power of 15 Gauss. Such extreme magnetism powers unique behaviors, including sudden, explosive releases of energy that rank among the most powerful short-duration events in the universe. To appreciate the extraordinary nature of magnetars, we must first understand neutron stars. These stellar remnants pack more mass than our Sun into a sphere roughly 20 kilometers in diameter. Their density defies intuition, equivalent to compressing Mount Everest into a sugar cube. At these densities, atoms cannot exist in their normal form. Instead, matter exists primarily as a sea of neutrons, hence the name neutron star. Neutron stars spin rapidly, completing a rotation in anywhere from milliseconds to seconds. They also possess strong magnetic fields, typically aligned off-axis from their rotation, causing them to sweep beams of radiation through space like cosmic lighthouses. When these beams sweep across Earth, we detect regular pulses of radiation, giving rise to the term pulsar for these regularly pulsing neutron stars. Magnetars, however, are neutron stars whose magnetic fields have been amplified to extreme levels. The origin of these powerful fields remains an area of active research. One theory suggests that some neutron stars are born spinning exceptionally fast, completing hundreds of rotations per second. In these conditions, turbulent motions within the newborn neutron star might amplify its magnetic field through a dynamo effect similar to, but far more intense than, the process that generates Earth's magnetic field. Whatever their origin, these extreme magnetic fields dominate the behavior of magnetars. The magnetic energy is so intense that it warps the outer crust of the neutron star and influences the surrounding space. The magnetic field lines twist and tangle, building tension like an overstretched elastic band. When this tension releases, either through small shifts in the magnetar's crust or through magnetic reconnection events similar to solar flares but vastly more powerful, enormous amounts of energy escape in various forms. These energy releases manifest as sudden outbursts that astronomers detect as soft gamma repeaters or anomalous X-ray pulsars, two observational categories now understood to represent different aspects of magnetar activity. During these outbursts, the magnetar's brightness can increase by a factor of thousands in less than a second, releasing more energy than our Sun produces in thousands or even hundreds of thousands of years. Perhaps the most dramatic example of magnetar power was demonstrated on December 27, 2004, when a giant flare from the magnetar SGR 1806-20 reached Earth. Despite originating from a source about 50,000 light-years away on the other side of our galaxy, this burst of energy was powerful enough to measurably affect Earth's upper atmosphere. For a brief moment, it outshone all other cosmic sources of X-rays and gamma rays combined. Had this event occurred within just 10 light-years of our solar system, it would have triggered a mass extinction event on Earth. This giant flare released more energy in a tenth of a second than our Sun releases in 100,000 years. The mechanism behind such extraordinary energy release lies in the magnetar's crust and magnetic field. The intense magnetic pressure can cause the solid crust of the neutron star to crack and shift, an event sometimes described as a starquake. This sudden reconfiguration releases stored magnetic energy, creating a fireball of plasma that expands at nearly the speed of light, emitting high-energy radiation in the process. The electromagnetic pulse from a magnetar flare is not its only explosive output. These events also produce fast radio bursts, millisecond duration pulses of radio emission, whose origins have long puzzled astronomers. While not all fast radio bursts come from magnetars, observations have confirmed that at least some of these enigmatic signals originate from magnetar flares, giving astronomers new insights into these mysterious radio flashes. Despite their explosive potential, magnetars are relatively rare in our galaxy. Astronomers have confirmed only about 30 magnetars in the Milky Way, though many more likely exist undetected. This rarity stems from their evolutionary path. Not every neutron star becomes a magnetar, and those that do maintain their extreme magnetic fields for a relatively brief cosmic period of about 10,000 years. After this time, the magnetic field decays, and the magnetar transitions into a more typical neutron star. The extreme conditions in and around magnetars make them natural laboratories for testing physics under conditions impossible to recreate on Earth. Their strong gravity warps space-time according to Einstein's general relativity. Powerful magnetic fields create environments where quantum electrodynamics predicts exotic effects like vacuum birefringence, where the vacuum itself behaves like a prism for light. The dense matter in their cores exists in states that challenge our understanding of nuclear physics. By studying magnetars, physicists gain windows into fundamental questions about the nature of matter, energy, and the universe itself. Magnetars also the elements. When neutron-rich material is ejected during particularly powerful flares, it can undergo rapid neutron capture processes, creating elements heavier than iron. While supernovae and neutron star mergers contribute more significantly to cosmic element production, magnetar activity adds another mechanism for enriching the interstellar medium with the building blocks of planets and life. The discovery of magnetars is relatively recent in astronomical history. The first soft gamma repeater was detected in 1979, but its nature remained mysterious for years. Only in the 1990s did theoretical work by Robert Duncan and Christopher Thompson establish the magnetar model, proposing that these objects were neutron stars with extraordinarily strong magnetic fields. Subsequent observations have confirmed this model and expanded our understanding of these extreme objects. Modern observations of magnetars utilize multiple instruments scanning different parts of the electromagnetic spectrum. Space-based X-ray and gamma-ray observatories like NASA's SWIFT, Fermi, and NICER provide detailed measurements of magnetar outbursts and their aftermath. Radio telescopes monitor for fast radio bursts and regular pulsations. Gravitational wave detectors search for ripples in space-time that might be produced by particularly violent magnetar starquakes. The evolution of magnetars connects them to other exotic stellar phenomena. Some magnetars may eventually evolve into rotation-powered pulsars as their magnetic fields decay. Others might experience sufficient mass gain through accretion to collapse into black holes. The relationships between different classes of neutron stars form a complex evolutionary network that astronomers are still mapping. Beyond their scientific significance, magnetars capture the imagination as some of the most extreme objects in the universe. Their combination of incredible density, rapid rotation, and magnetic fields stronger than any other known cosmic objects makes them stand out, even in a universe filled with extraordinary phenomena. They remind us that the cosmos still harbors objects and processes that push the boundaries of our physical understanding and technological capability to observe. As we drift among the stars in our mind's eye, consider the magnetars scattered throughout our galaxy, most hidden from direct view, but occasionally announcing their presence through bursts of radiation. These dense stellar corpses, seemingly quiet most of the time, harbor enormous reservoirs of magnetic energy waiting to be released. They represent a different kind of cosmic explosion, not the visible brilliance of a supernova or the focused beam of a gamma-ray burst, but the invisible strain of magnetic fields so powerful they can cause solid neutron star matter to crack and shift. Even a dead star can convulse, shaking space with invisible thunder. In the vast cosmic ballet, stellar remnants dance to the tune of gravity's pull. Among these remnants, neutron stars represent nature's attempt to compress matter to its limits, just shy of collapsing into black holes. When two of these extraordinarily dense objects meet in a catastrophic embrace, they create one of the universe's most violent and transformative events, a neutron star merger. Neutron stars begin their lives as the cores of massive stars that have exhausted their nuclear fuel and exploded as supernovae. What remains after this cataclysm is an object of extreme density, typically with a mass between 1.4 and 2 times that of our Sun, compressed into a sphere roughly 20 kilometers in diameter. A teaspoonful of neutron star material would weigh about 1 billion tons on Earth. These objects represent matter at its densest state before gravitational collapse would force it to become a black hole. Many neutron stars exist in binary systems, either paired with another neutron star, a white dwarf, a main sequence star, or in some cases, a black hole. These binary neutron star systems originate from massive binary stars that somehow survived the supernova explosions of both partners. After both stars have collapsed into neutron stars, they orbit their common center of mass, initially separated by vast distances compared to their size. What follows is a cosmic countdown measured in millions or billions of years. As the neutron stars orbit each other, they emit gravitational waves, ripples in the fabric of space-time, predicted by Einstein's theory of general relativity. These waves carry away orbital energy, causing the neutron stars to spiral gradually closer to each other. For most of their shared existence, this inward spiral proceeds imperceptibly slowly. A binary neutron star system might complete billions of orbits, losing energy through gravitational waves, before any dramatic changes occur. As the neutron stars draw closer, their orbital period shortens, and the rate of gravitational wave emission increases. This creates a feedback loop, with stronger gravitational wave emission leading to a faster inward spiral, which in turn generates even stronger gravitational waves. In the final minutes of their separate existence, this process accelerates dramatically. The neutron stars complete their last 1,000 orbits in mere seconds, whirling around each other at nearly the speed of light. The merger itself unfolds with astonishing speed. When the neutron stars finally touch, tidal forces distort their shapes, creating mountainous bulges in their otherwise nearly perfect spherical forms. Material from their outer layers can be flung outward by these tidal interactions, forming a surrounding cloud of neutron-rich matter. The cores of the two neutron stars then merge in less than a millisecond, releasing an enormous amount of energy in multiple forms. The immediate aftermath depends on the total mass of the merging neutron stars. If their combined mass exceeds a threshold of about 2.5 solar masses, the remnant will immediately collapse into a black hole. If the combined mass is lower, the result might be a hypermassive neutron star, temporarily supported against collapse by its rapid rotation. This object would eventually slow down and collapse into a black hole within seconds to hours after the merger. In rare cases with lower combined masses, the result might be a stable, massive neutron star that could persist indefinitely. One of the most dramatic outputs from a neutron star merger is a short-duration gamma-ray burst. As we explored in an earlier chapter, these intense flashes of high-energy radiation last less than 2 seconds and originate from jets of material accelerated to near light speed along the rotation axis of the merging system. The exact mechanism that launches these jets remains an area of active research, but likely involves the extreme magnetic fields of the neutron stars combined with the enormous energy released during the merger. Unlike long gamma-ray bursts associated with the deaths of massive stars, short gamma-ray bursts from neutron star mergers can occur in all types of galaxies, including those with little current star formation. This reflects the long delay between the formation of the neutron stars and their eventual merger, allowing the binary system to drift far from its birthplace or remain in galaxies where star formation has long since ceased. Beyond the gamma-ray burst, neutron star mergers produce another remarkable phenomenon called a kilonova. This optical and infrared afterglow results from the radioactive decay of heavy elements synthesized during the merger. The neutron-rich environment created when neutron star material is ejected provides ideal conditions for rapid neutron capture, or process nucleosynthesis, creating elements heavier than iron, including precious metals like gold and platinum, and radioactive elements like uranium and thorium. The role of neutron star mergers in creating heavy elements represents one of the most significant discoveries in modern astrophysics. For decades, astronomers believed that most heavy elements were forged in supernova. We now understand that neutron star mergers likely produce the majority of elements heavier than silver in the periodic table. The gold in your jewelry, the platinum in catalytic converters, and the uranium in nuclear reactors all likely originated in the violent collisions of neutron stars billions of years ago. The amount of heavy elements produced in a single neutron star merger is staggering. A typical event might generate an amount of gold equivalent to several times the mass of Earth, along with similar quantities of other precious metals. This material is flung into space at significant fractions of the speed of light, eventually mixing with interstellar gas and becoming incorporated into new generations of stars and planets. In a very real sense, we are adorned with the remnants of ancient neutron star collisions. The theoretical predictions about neutron star mergers received dramatic confirmation on August 17, 2017, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves from a neutron star merger designated GW170817. 7 seconds after the gravitational wave signal peaked, the Fermi Gamma-Ray Space Telescope detected a short gamma-ray burst from the same direction. Within hours, optical telescopes located the kilonova in a galaxy called NGC 4993, about 130 million light-years from Earth. This event, the first neutron star merger detected through both gravitational waves and electromagnetic radiation, marked the birth of multi-messenger astronomy. By combining information from gravitational waves, which provide details about the masses and spins of the merging objects, with observations across the electromagnetic spectrum, astronomers gained unprecedented insights into the physics of neutron star mergers. The kilonova observations confirmed the production of heavy elements, including detection of spectral signatures consistent with newly synthesized gold and platinum. The study of neutron star mergers connects many branches of physics and astronomy. Nuclear physicists use these events to investigate the behavior of matter at densities impossible to create in terrestrial laboratories. Gravitational wave astronomers extract information about the equation of state of neutron star matter from the gravitational waveforms leading up to the merger. Astronomers studying galactic chemical evolution use neutron star mergers to understand how heavy elements have been distributed throughout cosmic history. Beyond their role in element production, neutron star mergers contribute to our understanding of fundamental physics. The near-simultaneous arrival of gravitational waves and electromagnetic radiation from GW 170817 confirmed that gravitational waves travel at the speed of light, constraining alternative theories of gravity. The neutrinos produced during the merger, though not detected from this event, offer another messenger that could provide complementary information in future detections. The rate of neutron star mergers in our galaxy and throughout the universe remains somewhat uncertain. Based on gravitational wave detections and observations of short gamma-ray bursts, astronomers estimate that a neutron star merger occurs somewhere in the observable universe roughly every 10 seconds. In our Milky Way galaxy, such mergers might happen once every 10,000 to 100,000 years. While rare locally, these events have occurred frequently enough over cosmic history to account for the abundance of heavy elements we observe. The future of neutron star merger observations looks promising. As gravitational wave detectors improve in sensitivity, they will detect these events from greater distances and with better precision. Space-based gravitational wave observatories planned for the coming decades will extend the observable frequency range, potentially tracking binary neutron stars throughout their inspiral phase. Coordination between gravitational wave facilities and electromagnetic observatories continues to improve, increasing the likelihood of capturing the complete picture of future merger events. Computer simulations of neutron star mergers have also advanced dramatically, allowing scientists to model the complex interplay of extreme gravity, nuclear physics, magnetohydrodynamics, and relativistic effects. These simulations predict the gravitational wave signals, electromagnetic emissions, and nucleosynthesis outputs that can be compared with observations. Each new detection helps refine these models, creating a virtuous cycle of improvement in our theoretical understanding. As we contemplate these cosmic collisions, we witness nature's most extreme laboratory. Two objects, each containing more mass than our Sun compressed into the size of a city, spiraling together over millions of years, their final union releasing more energy in seconds than most stars emit in millennia. From this violence comes creation, as the debris enriches the cosmos with the elements necessary for planets and life. The gold that humans have valued throughout history represents the aftermath of cataclysms beyond our ancestors' wildest imagination. Two dense remnants circling ever closer until at last they touch, and the universe listens. In the pantheon of cosmic violence, few events rival the merger of two black holes. Unlike the spectacular electromagnetic displays of supernovae or the heavy element forges of neutron star collisions, black hole mergers unfold in darkness, invisible to traditional telescopes. Yet these silent cataclysms represent some of the most energetic events in the universe, sending ripples through the very fabric of space-time that carry more power than all the stars in the observable cosmos combined. Black holes represent the ultimate victory of gravity over all other forces in nature. When sufficient mass concentrates in a small enough volume, not even light can escape its gravitational pull, leading to the formation of an event horizon, a boundary beyond which nothing can return. Inside this horizon lies a singularity, a point where our current understanding of physics breaks down, where space and time as we understand them cease to exist in any meaningful sense. Black holes come in several varieties. Stellar mass black holes form from the collapsed cores of massive stars, typically containing between 5 and 100 times the mass of our Sun. Intermediate mass black holes, with masses between 100 and 100,000 solar masses, likely form through the mergers of smaller black holes, or from the direct collapse of massive gas clouds in the early universe. Supermassive black holes, containing millions to billions of solar masses, lurk at the centers of most galaxies, including our Milky Way. Each type can participate in merger events, though the processes and timescales differ. Like neutron stars, Black holes can exist in binary systems. Some binary black holes begin as massive binary stars that each form a black hole at the end of their lives. Others form through dynamic encounters in dense stellar environments like globular clusters, where gravitational interactions can bring previously unrelated black holes into bound orbits. Still others might form when already existing black holes encounter each other in the crowded central regions of galaxies. Once two black holes form a bound binary system, their fate is sealed by the emission of gravitational waves. As the black holes orbit each other, they generate ripples in spacetime that radiate energy and angular momentum away from the system. This causes the black holes to spiral gradually closer, initially over timescales of millions or billions of years. As the separation decreases, the orbits accelerate, and the gravitational wave emission intensifies, creating the same feedback loop we described for neutron star binaries. The final moments of a black hole merger proceed with dramatic swiftness. In the last few orbits, the black holes reach significant fractions of the speed of light as they whirl around their common center of mass. The gravitational waves generated during this final in-spiral phase carry away enormous amounts of energy, briefly making the merging system the most powerful gravitational wave source in the observable universe. At the moment of merger, the black holes coalesce into a single, more massive black hole that typically undergoes a brief period of vibration called ring down before settling into its final state. Unlike many other cosmic explosions, black hole mergers do not directly produce electromagnetic radiation. With no matter to heat and no light to emit, these events were long considered invisible, detectable only through their gravitational wave signatures. However, if the merging black holes exist in gas-rich environments, such as active galactic nuclei, the surrounding material might produce observable electromagnetic counterparts as it responds to the changing gravitational field and the final merger. The energy released during a black hole merger staggers the imagination. When two black holes merge, a portion of their combined mass, typically around 5%, converts directly into gravitational wave energy, according to Einstein's famous equation E equals mc squared. For a merger of 230 solar mass black holes, this means about 3 solar masses worth of energy radiates away as gravitational waves in a fraction of a second. This energy output exceeds the combined light output of all the stars in the observable universe during that brief moment. The first direct detection of gravitational waves, announced in February 2016 by the LIGO and Virgo collaborations, came from precisely such an event, 3 billion light-years from Earth. This historic detection not only confirmed a key prediction of Einstein's general relativity, but also inaugurated the era of gravitational wave astronomy, opening a new window on the universe. Since that first detection, gravitational wave observatories have recorded dozens more black hole mergers with a wide range of masses and distance. Each detection provides information about the masses and spins of the merging black holes, their approximate location in the sky, and their distance from Earth. Collectively, these observations are building a census of black hole populations throughout cosmic history, revealing surprising features such as black holes in mass ranges once thought impossible, according to stellar evolution theory. Black hole mergers across cosmic time have played a crucial role in the formation of the supermassive black holes we observe at the centers of galaxies today. The growth of these cosmic behemoths likely involved a combination of gas accretion and mergers with other black holes. When galaxies collide, their central black holes eventually find each other through a process called dynamical friction, where the black holes gradually lose orbital energy as they interact with surrounding stars. After coming within about a light year of each other, gravitational wave emission takes over to bring them to their final merger. The gravitational waves from merging supermassive black holes have frequencies too low to detect with current ground-based interferometers like LIGO and Virgo. Future space-based gravitational wave observatories, such as the Laser Interferometer Space Antenna, or LISA, will operate in the frequency range needed to observe these titanic collisions. LISA and similar facilities will potentially detect thousands of supermassive black hole mergers throughout the observable universe, providing unprecedented insights into galaxy formation and evolution. The merger of black holes connects to deeper questions about the nature of gravity, space, and time. According to general relativity, The intense gravitational fields during a merger cause significant distortions of space-time. If we could somehow observe the region around merging black holes, we would see space itself stretching and compressing, light paths bending in complex ways, and time flowing at different rates in different locations. These extreme conditions test our theories of gravity in regimes where quantum effects might become important, potentially providing clues to a future quantum theory of gravity. The detection of gravitational waves from black hole mergers represented one of the greatest achievements in modern physics and astronomy. The technical challenges involved were enormous, requiring the ability to measure changes in distance smaller than the width of a proton over kilometer-scale interferometer arms. The current generation of detectors continues to improve in sensitivity, promising many more detections in the coming years. Future facilities, both on Earth and in space, will extend the observable frequency range and potentially detect many thousands of merger events annually. As we ponder these dark, invisible collisions, we confront the limits of our intuition. Black holes represent regions where reality as we understand it breaks down, where the mathematics of general relativity points toward infinities our theories cannot yet resolve. In their collisions, we witness not explosions of light and matter, but distortions of space and time themselves. Though invisible to our eyes, these events speak to our scientific instruments through the subtle squeezing and stretching of the cosmic fabric that connects all things. There is no light, only the tremble of existence itself. Moving beyond the violent deaths of stars and the collisions of their remnants, we now turn our attention to phenomena that operate on an even grander scale, the explosive activity at the centers of galaxies. Here, in the crowded cores of vast stellar cities, lurk objects of almost unfathomable power and darkness, supermassive black holes. When these cosmic leviathans feed, they produce some of the most luminous sustained objects in the universe, quasars. The term quasar derives from quasi-stellar radio source, reflecting how these objects were first identified in the late 1950s. Early radio astronomers detected strong radio emissions from sources that, when observed with optical telescopes, appeared star-like rather than extended like galaxies. The mystery deepened when spectra from these objects revealed unusual emission lines at wavelengths that did not match any known elements. The solution came in 1963, when astronomer Martin Schmidt realized that the spectrum of the quasar 3C273 showed ordinary hydrogen lines, but dramatically redshifted, indicating that this object was retreating from Earth at about 15% of the speed of light. This implied an extraordinary distance and, consequently, an extraordinary luminosity. We now understand that quasars represent a phase in galactic evolution during which the central supermassive black hole actively consumes surrounding material. All large galaxies, including our Milky Way, appear to harbor central black holes with masses ranging from millions to billions of times that of our Sun. Most of these black holes are relatively quiet in the present cosmic epoch, consuming only small amounts of material and emitting relatively little radiation. But when ample fuel becomes available, typically following galactic mergers or other processes that funnel gas toward the galactic center, these sleeping giants awaken with spectacular consequences. The mechanism that powers a quasar begins with a swirling disk of gas and dust called an accretion disk, which forms around the supermassive black hole. As material in this disk spirals inward, gravitational potential energy converts to heat through friction and other dissipative processes. The inner regions of the disk can reach temperatures of tens of thousands to millions of degrees, causing the disk to glow brightly across the electromagnetic spectrum, with particular intensity in ultraviolet and X-ray wavelengths. The efficiency of this process explains the extraordinary luminosity of quasars. A typical quasar might convert about 10% of the rest mass energy of the infalling material into radiation, far more efficient than the roughly 1% conversion of nuclear fusion that powers stars. For comparison, a quasar consuming just one solar mass of material per year can outshine 1 trillion suns, emitting more light than all the stars in several Milky Way-sized galaxies combined. This prodigious energy output makes quasars visible across vast cosmic distances. The most distant confirmed quasar, J0313-1806, exists at a redshift of 7.64, meaning we see it as it was when the universe was just 670 million years old, less than 5% of its current age. The light from this ancient cosmic beacon has traveled for more than 13 billion years before reaching our telescopes, providing a glimpse of conditions in the very early universe. The supermassive black holes that power quasars raise profound questions about cosmic evolution. Their existence in the early universe challenges our understanding of black hole formation and growth, as conventional processes struggle to explain how black holes of billions of solar masses could form in the relatively short time available. Leading theories suggest that the first black hole seeds might have formed from the direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely, or from the rapid mergers of multiple stellar mass black holes in dense environments. The region surrounding a feeding supermassive black hole creates some of the most extreme environments known to science. Beyond the accretion disk lies a broader region of gas clouds illuminated by the intense radiation from the inner disk. These clouds, moving at thousands of kilometers per second in the black hole's gravitational field, produce the distinctive broad emission lines seen in quasar spectra. Further out, a dusty torus often surrounds the inner regions, partially obscuring the accretion disk when viewed from certain angles and absorbing and re-emitting its energy as infrared radiation. Perhaps most dramatically, many quasars and their less luminous cousins, active galactic nuclei, produce spectacular jets of material that can extend far beyond the host galaxy. These jets form when some of the infalling material, rather than crossing the event horizon, gets channeled along the black hole's rotational axis and accelerated to near light speed. Powered by the black hole's gravity and shaped by its magnetic field, these jets can stretch for hundreds of thousands or even millions of light years, making them among the largest coherent structures in the universe. The energy carried by these jets can profoundly influence their surroundings. When the jets interact with gas in the host galaxy or the surrounding intergalactic medium, they create shock waves that compress and heat the gas, potentially both triggering and suppressing star formation. This process, called active galactic nucleus feedback, plays a crucial role in galaxy evolution, helping explain the observed relationship between black hole mass and galaxy properties. Quasars do not shine eternally. The active phase typically lasts for about 10 million to 100 million years, a mere blink in cosmic terms. During this time, the supermassive black hole might grow substantially, adding millions or billions of solar masses to its total. Eventually, the available fuel supply diminishes, either consumed by the black hole or blown away by the intense radiation and jets. The quasar then fades, leaving behind a more massive central black hole in a galaxy that has been fundamentally altered by the episode of intense activity. The life cycle of quasars appears intimately connected to the evolution of galaxies. Observations suggest that most large galaxies have gone through one or more quasar phases during their history. Our own Milky Way's central black hole, Sagittarius A star, with its relatively modest 4 million solar masses, likely experienced periods of quasar-like activity in the distant past. Evidence for this includes the Fermi bubbles, large structures extending above and below the galactic plane that may represent the remnants of ancient outflows from our once more active galactic center. Studies of quasar populations throughout cosmic history reveal a peak in activity around 10 to 12 billion years ago, when the universe was about a quarter of its current age. This epoch, sometimes called cosmic noon, saw intensive star formation and galaxy growth across the universe. Since then, the density of quasars has declined dramatically, reflecting both the decreasing availability of fresh gas supplies and the growth of most supermassive black holes to their near-final masses. Modern astronomical techniques allow scientists to study quasars in unprecedented detail. Large sky surveys have identified hundreds of thousands of quasars across cosmic history, creating statistical samples that trace their evolution. Interferometric radio observations can resolve the structure of jets on various scales, revealing their dynamics and interaction with surrounding media. X-ray observations probe the hot inner regions of the accretion disk, while infrared telescopes peer through the obscuring dust to study the central engine and its surroundings. Perhaps most exciting, Gravitational wave observatories will soon provide a new window into the formation and evolution of the supermassive black holes that power quasars. When pairs of these behemoths merge following the collision of their host galaxies, they generate gravitational waves of much lower frequency than those from stellar mass black hole mergers. Future space-based interferometers will detect these waves, providing direct measurements of black hole masses and spins throughout cosmic history. The study of quasars connects to fundamental questions in cosmology, galaxy evolution, and black hole physics. How did the first supermassive black holes form in the early universe? How do black holes and galaxies influence each other's growth? What are the physical conditions in the extreme environments near feeding black holes? Each new observation and theoretical advance brings us closer to answering these questions, unraveling the story of these cosmic beacons. As we contemplate these galactic powerhouses, we recognize another facet of nature's propensity for recycling. The material falling into a quasar's central black hole does not simply disappear. Some of it powers radiation and jets that influence gas clouds throughout the host galaxy and beyond, potentially triggering the formation of new stars and planets. The elements synthesized in these stars will eventually return to the interstellar medium, perhaps to be incorporated into future generations of stars, or, in some cases, to fall once again toward the central black hole, continuing the cosmic cycle. In the quiet heart of a galaxy, sometimes a monster awakens. Having explored the central engines of quasars, we now focus our attention on one of their most spectacular features, the relativistic jets that extend from active galactic nuclei. These narrow beams of plasma, accelerated to near light speed, represent some of the most powerful sustained outflows in the universe, carrying energy, magnetic fields, and particles across intergalactic distances. And when one of these cosmic searchlights happens to point directly at Earth, we observe the most extreme class of active galactic nuclei, blazars. Active galactic nuclei, or AGN, is the broader term encompassing all manifestations of supermassive black hole activity at galactic centers. Quasars represent the most luminous subclass of AGN, but other categories exist, distinguished by their luminosity, spectral characteristics, and the presence or absence of jets. These jets form one of the most distinctive and influential features of many AGN, visible across the electromagnetic spectrum, but particularly prominent in radio wavelengths. The formation of these jets remains one of the most fascinating puzzles in astrophysics. The basic process involves material from the accretion disk being channeled along the black hole's rotational axis and accelerated to relativistic speeds. However, the exact mechanisms involve complex interactions between gravity, magnetic fields, and plasma dynamics in the extreme environment near the event horizon. Leading theories suggest that twisted magnetic fields anchored in the rapidly spinning accretion disk, or the ergosphere of the rotating black hole itself, play a crucial role in launching and collimating these outflows. Once launched, AGN jets can extend across truly vast distances. The jets from the radio galaxy Hercules A stretch more than 1.5 million light-years from the central black hole, more than 15 times the diameter of the entire Milky Way galaxy. If human eyes could see radio waves, these jets would appear larger than the full moon in our sky, despite being located about 2 billion light-years from Earth. Such enormous structures underscore the extraordinary power of the central engines that create them. The material in these jets travels at speeds exceeding 99% of the speed of light. At such velocities, the effects of Einstein's special relativity become pronounced. Time dilation slows the apparent evolution of the jet from our perspective. Length contraction compresses the jet along its direction of motion. Most dramatically, relativistic beaming concentrates the radiation in the forward direction, making the jet appear much brighter when pointed toward us and much fainter when pointed away. This relativistic beaming effect explains the extreme properties of blazars, AGN, where one jet points almost directly at Earth. In blazars, the observed emission becomes dominated by the jet rather than the accretion disk or surrounding regions. The radiation appears greatly amplified, and rapid variations in the source brightness become apparent, sometimes changing by factors of several over timescales of hours or even minutes. These variations do not indicate changes in the overall power output, but rather localized fluctuations greatly magnified by the relativistic effects. Blazars represent relatively rare configurations, as the narrow jets from AGN will randomly orient toward Earth in only a small fraction of cases. However, their extreme brightness makes them detectable across vast cosmic distances, allowing astronomers to study the evolution of active galaxies throughout much of cosmic history. The most distant confirmed blazar, PSOJ 030947.9 plus 271045, shines from when the universe was less than 1 billion years old, demonstrating that powerful jets formed early in cosmic evolution. The electromagnetic radiation from AGN jets spans the entire spectrum, from radio waves to gamma rays. This broad emission profile results from multiple radiation mechanisms operating within the jets. Synchrotron radiation, produced when electrons spiral around magnetic field lines, dominates at radio through optical wavelengths. At higher energies, processes like inverse Compton scattering, where relativistic electrons boost low-energy photons to much higher energies, become important. In the most powerful blazars, gamma rays with energies of trillions of electron volts have been detected, making these among the most energetic photons observed from any cosmic source. The study of AGN jets connects to broader questions about cosmic particle acceleration. The conditions within these jets create natural particle accelerators far more powerful than anything built on Earth. Protons and electrons can reach energies millions or billions of times greater than those achieved in the Large Hadron Collider. Some scientists suspect that the most energetic cosmic rays, subatomic particles that strike Earth's atmosphere with extraordinary energies, originate in the jets of active galaxies, though this connection remains an active area of research. When AGN jets interact with the surrounding intergalactic medium, they create spectacular structures visible in radio images. The jet material, traveling at relativistic speeds, slams into the much slower ambient gas, creating shockwaves that inflate enormous lobes of radio-emitting plasma. These radio lobes can extend far beyond the visible boundaries of the host galaxy, sometimes reaching diameters of several million light-years. The morphology of these structures, classified as Fanaroff-Riley Type 1 or Type Tekard, based on their brightness distribution, provides clues to the power of the central engine and the density of the surrounding medium. Beyond their astronomical significance, AGN jets play important roles in galaxy evolution and cosmic ecology. The energy they inject into their surroundings can heat intergalactic and intra-cluster gas, potentially preventing it from cooling and forming new stars. This process, known as AGN feedback, helps regulate star formation in massive galaxies and may explain why the most massive galaxies contain primarily old stellar populations. Conversely, the compression of gas clouds by jet-induced shockwaves can sometimes trigger star formation in specific regions, creating a complex balance of influences. The classification of AGN into various subtypes reflects not just intrinsic differences, but also our viewing angle relative to the jets and obscuring structures. According to unification models, many of the historical categories of AGN, such as radio galaxies, quasars, and blazars, represent the same basic phenomenon viewed from different perspectives. From this viewpoint, a blazar represents an AGN observed nearly along the jet axis, while a radio galaxy represents a similar system viewed from the side, where the relativistic beaming effects do not enhance the jet brightness. Different subclasses of blazars exist, primarily distinguished by their spectral properties. BL Lacertae objects, named after the first identified member of the class, show weak or absent emission lines, suggesting relatively little gas around the central engine. Flat-spectrum radio quasars, by contrast, display stronger emission lines, indicating more substantial surrounding gas clouds illuminated by the central source. These differences likely reflect variations in the accretion rate, jet power, and surrounding environment among different AGN. Our own galaxy harbors a supermassive black hole, Sagittarius A star, that currently displays only minimal activity. However, evidence suggests that the Milky Way has experienced more active phases in the past. The Fermi bubbles, large structures extending about 25,000 light-years above and below the galactic center, may represent the remnants of past jet activity from our central black hole. If our galaxy were to experience renewed AGN activity in the distant future, it might eventually develop the dramatic jets we observe in more active galaxies. The study of AGN jets and blazars has been revolutionized by multi-wavelength and multi-messenger astronomy. Modern radio interferometers like the Very Long Baseline Array can resolve the structure of jets on scales smaller than a light-year, even in distant galaxies. Space observatories operating at X-ray and gamma-ray wavelengths detect the high-energy emission from the most energetic regions of the jets. Neutrino observatories have recently detected high-energy neutrinos from the direction of blazars, opening a new channel for studying these exotic objects. As we contemplate these cosmic fountains, stretching across millions of light years and persisting for millions of years, we witness nature operating on scales that challenge human comprehension. The jets from active galactic nuclei represent the influence of black holes, the darkest objects in the universe, reaching far beyond their immediate surroundings to shape the evolution of galaxies and the intergalactic medium. Through their extended lifetimes, they transform the cosmic landscape, redistributing energy across vast distances and potentially influencing the formation of future generations of stars and galaxies. Even in the dark, galaxies breathe fire across interstellar oceans. Throughout our cosmic journey, we have explored explosions of increasing scale and energy, from stellar deaths to galaxy core eruptions. Now we arrive at the ultimate cosmic event, the explosion that gave birth to everything, the Big Bang. Yet this primordial cataclysm differs fundamentally from all others we have discussed. It was not an explosion in space, but an explosion of space itself, the moment when our universe as we know it began. The concept of the Big Bang emerged gradually during the 20th century, built upon multiple lines of evidence and theoretical insights. In the 1920s, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, with their recession velocities proportional to their distances. This observation suggested an expanding universe, which when projected backward in time, implied a beginning when all matter was concentrated in an extremely dense, hot state. The term Big Bang, ironically, was coined by astronomer Fred Hoyle, who advocated for a competing steady-state theory and intended the name somewhat dismissively. Yet the evidence for the Big Bang continued to accumulate. In 1964, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. This discovery, along with the successful prediction of the primordial abundances of light elements like hydrogen, helium, and lithium, firmly established the Big Bang as the standard model of cosmology. Unlike the other explosions we have explored, the Big Bang did not occur at a specific location in pre-existing space. There was no outside to the explosion, no center from which it expanded. Instead, space itself came into existence and began expanding, carrying matter and energy with it. Every point in the universe can be considered the center of the expansion, as seen from that point. This counterintuitive concept challenges our everyday understanding of explosions, but follows directly from Einstein's general theory of relativity, our best description of gravity and space-time. The earliest moment of the Big Bang remains shrouded in mystery. Our current physics becomes inadequate to describe conditions when the universe was younger than about 10 to the negative 43 seconds, a vanishingly brief instant known as the Planck time. At this epoch, quantum effects in gravity become dominant, requiring a quantum theory of gravity that remains beyond our current theoretical framework. This limitation creates a horizon of knowledge before which we cannot currently peer with confidence. From the end of the Planck epoch onwards, however, we can trace the universe's evolution with increasing certainty. The earliest phase for which we have a coherent theoretical description is cosmic inflation, a period of exponential expansion that occurred when the universe was about 10 to the negative 36 seconds old. During this incredibly brief moment, the universe expanded faster than light speed, increasing in size by a factor of at least 10 to the 26th power. This expansion smoothed out irregularities and established the large-scale uniformity we observe in the cosmos today, while quantum fluctuations during inflation seeded the tiny variations in density that would eventually grow into galaxies and larger structures. When inflation ended, the energy that drove the expansion converted into particles and radiation in a process called reheating. The universe was now filled with an ultra-hot, ultra-dense plasma of fundamental particles, with temperatures exceeding 10 to the 27 degrees Celsius. This marks the beginning of the hot Big Bang phase that most people associate with the term Big Bang itself. As the universe continued to expand and cool, it passed through a series of transitions, each marking the emergence of new physics. When the universe was about 1 microsecond old and had cooled to about 10 trillion degrees, quarks combined to form protons and neutrons. By the time the universe reached 1 second of age at a temperature of about 10 billion degrees, the lightest elements began to form in a process called Big Bang nucleosynthesis. Protons and neutrons fused to create deuterium, helium, and trace amounts of lithium, establishing the primordial composition of the cosmos that would persist until the first stars formed hundreds of millions of years later. For the first 380,000 years, the universe remained opaque, with light constantly scattering off free electrons in the hot plasma. But as the expansion continued and temperatures fell below about 3,000 degrees, electrons combined with nuclei to form neutral atoms, primarily hydrogen and helium. This event, known as recombination, allowed photons to travel freely for the first time. These ancient photons continue their journey today, detected as the cosmic microwave background radiation, a perfect snapshot of the infant universe just as it became transparent. The cosmic microwave background appears remarkably uniform, with temperature variations of only about 1 part in 100,000. Yet these tiny fluctuations contain the seeds of all cosmic structure. Regions with slightly higher density exerted slightly stronger gravitational pulls on surrounding matter, gradually amplifying the initial differences. Over hundreds of millions of years, these small overdensities grew into the first stars and galaxies, beginning the grand process of cosmic structure formation that continues to the present day. About 100 million years after the Big Bang, the universe entered a transformative period known as the Cosmic Dawn. In the darkness that had persisted since recombination, the first stars ignited, massive, short-lived beacons of light that began to reionize the neutral hydrogen that filled space. These population 3 stars, composed almost entirely of hydrogen and helium, lived brief, brilliant lives before exploding as supernovae, seeding their surroundings with the first heavy elements. The cycle of stellar birth, life, and death that we explored in earlier chapters had begun. Over the next few hundred million years, the first galaxies formed, small, irregular collections of stars that would eventually merge to form larger structures. Supermassive black holes began to grow in their centers, some becoming the powerful quasars we discussed previously. The intergalactic medium, meanwhile, was gradually reionized by the combined radiation from stars and active galactic nuclei, a process completed by about 1 billion years after the Big Bang. The universe we observe today, about 13.8 billion years after the Big Bang, retains the imprint of its explosive birth, while displaying the rich complexity that has evolved since then. The expansion discovered by Hubble continues and, surprisingly, is accelerating, driven by a mysterious dark energy that constitutes about 68% of the universe's current energy content. Dark matter, which interacts through gravity but not electromagnetically, makes up about 27%, while the ordinary matter that comprises stars, planets, and life constitutes a mere 5% of the cosmic inventory. The Big Bang theory successfully explains numerous observations that would otherwise remain mysterious. The expansion of the universe, the cosmic microwave background, the primordial abundance of light elements, the large-scale structure of the cosmos, and the distribution of galaxies all align with its predictions. Yet questions remain. What caused inflation? What is the nature of dark energy and dark matter? Did anything exist before the Big Bang? These frontier questions drive ongoing research in theoretical physics and observational cosmology. Unlike the other explosions we have explored, we cannot directly observe the Big Bang itself. Its light has been redshifted by the expansion of space far beyond the range of our instruments, and much of the crucial physics occurred before the universe became transparent. Instead, we piece together the story through a combination of theoretical models, computer simulations, and observations of the cosmic microwave background and other relics. The James Webb Space Telescope, launched in 2021, allows astronomers to peer closer to the Big Bang than ever before. observing galaxies that formed when the universe was just a few 100 million years old. Future gravitational wave observatories may detect signatures from the earliest epochs, potentially including inflation itself. Each new observation refines our understanding of cosmic history, filling in details of the grand narrative that began with the Big Bang. The Big Bang represents not just the birth of our universe, but the origin of time itself as we understand it. Whether time existed in some form before the Big Bang remains speculative, venturing into realms where physics meets philosophy. Some theoretical frameworks suggest a universe that bounces through successive cycles of expansion and contraction, while others propose a multiverse of bubble universes nucleating from a larger cosmos. These ideas remain speculative, pushing the boundaries of current scientific knowledge. As we contemplate the Big Bang, we confront the limits of our understanding. The conditions of the early universe were so extreme, so different from anything we can recreate in laboratories, that they challenge our physical theories and our imagination. Yet through mathematics, observations, and logical inference, we have constructed a remarkably detailed account of how our universe evolved from its earliest moments to the rich complexity we observe today. The Big Bang differs from all other cosmic explosions in its uniqueness. While supernovae, gamma-ray bursts, and even galaxy mergers occur repeatedly throughout the universe, there was only one Big Bang that gave rise to our observable cosmos. It represents the ultimate boundary of our knowledge, the horizon beyond which our current science cannot penetrate with confidence. In its aftermath, all other cosmic processes unfold. The elements forged in stellar explosions were made possible by the primordial hydrogen and helium from the Big Bang. The black holes that power quasars and emit gravitational waves when they merge exist within the expanding space-time that originated in that first moment. The complex chemistry that enables life on Earth traces its origins to the fundamental forces and particles established in the early universe. All explosions since are echoes, shadows, fragments of that first great awakening. We have journeyed from the explosive deaths of stars to the birth of the universe itself. Now our cosmic voyage reaches its final destination, the ultimate fate that awaits not just individual celestial bodies, but the entirety of existence. As with all stories, the universe itself has a beginning, middle, and end. Having explored its explosive beginning and dynamic middle, we now turn our gaze toward the distant horizon of cosmic time to contemplate its end. The fate of the universe is written in its expansion, a process that has continued since the Big Bang. For decades, astronomers debated whether this expansion would eventually slow and reverse, leading to a big crunch, or continue forever, leading to a big freeze. The discovery in the late 1990s that the expansion is actually accelerating, driven by mysterious dark energy, has profound implications for our cosmic destiny. This acceleration suggests that the universe will expand forever, growing increasingly vast and increasingly empty. In the near cosmic future, meaning the next few billion years, life in our galaxy will proceed relatively unchanged. Our Milky Way, however, is on a collision course with the neighboring Andromeda galaxy. About 4.5 billion years from now, around the time our Sun will exhaust its core hydrogen and begin to expand into a red giant, these two spiral galaxies will merge. Their hundreds of billions of stars will engage in a gravitational dance, eventually settling into a single, large elliptical galaxy that astronomers have preemptively named Milkomeda. Over the next trillion years, star formation throughout the universe will gradually slow as the available gas becomes depleted. New stars will become increasingly rare, while existing stars will exhaust their fuel and expire. Red dwarf stars with their miserly energy usage will be the last to go, some persisting for up to 10 trillion years. Eventually, however, the universe will go dark as the last stars fade away, leaving behind white dwarfs, neutron stars, and black holes. This stellar apocalypse marks not the end, but merely the beginning of the end. The universe will then enter what cosmologists call the degenerate era, lasting from about 10 to the 14 to 10 to the 36 years from now. During this unimaginably long period, stellar remnants will dominate the cosmos. White dwarfs will slowly cool, their once fierce heat radiating away into the ever-expanding void. Occasional rare events will briefly illuminate this darkness, such as collisions between stellar remnants or the destruction of planets that wander too close to dead stars. Even these cold remnants are not truly eternal. According to the standard model of particle physics, protons, the building blocks of atomic nuclei, may be unstable over extremely long timescales. Current experiments suggest that if protons do decay, their half-life exceeds 10 to the 34 years, an incomprehensibly long period. But in the vastness of cosmic time, even such stability is temporary. If proton decay occurs, white dwarfs and neutron stars will eventually dissolve, their fundamental particles breaking down into radiation and lighter particles. Meanwhile, black holes of all sizes will continue their slow growth, occasionally consuming wayward matter or merging with other black holes in events detectable as gravitational waves. But even these cosmic vacuum cleaners cannot escape the laws of quantum mechanics. Stephen Hawking discovered that black holes must emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly feeble for large black holes, but over the vast stretches of time ahead, it will become significant. The universe will then enter the black hole era, spanning from about 10 to the 36 to 10 to the 100 years from now. During this era, black holes will dominate the cosmic landscape as virtually the only structured objects remaining. These dark behemoths will slowly evaporate through Hawking radiation, with smaller black holes disappearing first. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate completely, while the supermassive black holes at galaxy centers might persist for up to 10 to the 100 years, releasing their stored energy as increasingly energetic radiation as they shrink. The final evaporation of a black hole would release a burst of high-energy radiation, a last farewell from these cosmic giants. In this far future universe, such events would be the only significant energy releases, the final fireworks in an otherwise cold and dark cosmos. They would briefly illuminate a universe otherwise dominated by diffuse radiation and fundamental particles, separated by ever-increasing distances due to the continuing cosmic expansion. Following the black hole era comes what cosmologists call the dark era, extending from 10 to the 100 years to effectively infinity. In this final phase, the universe will consist almost entirely of photons, neutrinos, electrons, and positrons, all massively redshifted by expansion and exceedingly cold. Occasionally, quantum fluctuations might bring particles together to form unstable atoms, but these would rapidly dissolve back into the void. The universe would reach a state of near-perfect entropy, with energy evenly distributed and almost no capacity for further structured processes. This picture of accelerating expansion leading to a cold, dark fate is our current best understanding based on observations of dark energy. However, the nature of dark energy remains one of physics' greatest mysteries. If dark energy were to change its behavior in the future, alternative cosmic fates become possible. One alternative is the Big Rip scenario. If dark energy were to grow stronger over time, it could eventually become powerful enough to tear apart galaxies, then solar systems, then planets, and ultimately atoms themselves. The universe would end in a catastrophic shredding of all structures down to the subatomic level. Another possibility is the Big Crunch, which could occur if dark energy were to somehow reverse its effects, allowing gravity to eventually halt and reverse the cosmic expansion. The universe would then collapse back on itself. Temperatures and densities would rise, and everything would compress into a state similar to the Big Bang, perhaps seeding another cycle of cosmic existence. A third alternative is the Big Bounce, where the universe cycles through expansions and contractions, with each Big Crunch leading to a new Big Bang. Such cyclical models appeal to some because they avoid the problem of explaining a singular beginning and end to time itself. Some speculative theories even suggest the possibility of false vacuum decay, where our universe exists in a metastable state that could tunnel to a lower energy configuration. This would unleash a bubble of new vacuum that would expand at the speed of light, rewriting the laws of physics in its wake and effectively ending our universe as we know it. These alternatives remain speculative, with the weight of current evidence favoring the Big Freeze scenario of eternal expansion. Regardless of which cosmic fate awaits, the timescales involved stretch human comprehension to its limits. The universe as we know it, filled with stars, galaxies, and the possibility for planets and life, represents a relatively brief middle chapter in a much longer cosmic story. As we contemplate these distant futures, we might wonder about the significance of our moment in cosmic history. We live in what astronomers call the stelliferous era, the age of stars, a period when structured matter and available energy make complex phenomena like life possible. This era constitutes less than 1% of the universe's potential future timeline, a brief window when the conditions for our existence are met. In this cosmic perspective, the explosive phenomena we have explored throughout our journey, from supernova to gamma-ray bursts to the active cores of galaxies, represent the universe at its most dynamic and creative. These violent events, rather than being aberrations, are essential aspects of a cosmos that evolves through cycles of creation and destruction. The elements that compose our bodies were forged in stellar furnaces and scattered by ancient explosions. The energy that powers our sun and sustains life on Earth derives ultimately from the gravitational potential established in the Big Bang. All things that explode eventually fade, but even endings hold beauty. As our journey through the most powerful explosions in the universe comes to a close, we find ourselves reflecting on a profound paradox. Throughout cosmic history, destruction and creation have been inseparably intertwined, each making the other possible in an eternal cosmic dance. The violent deaths of stars seed the cosmos with heavy elements necessary for planets and life. The collisions of neutron stars scatter gold and platinum across interstellar space. The outflows from active galactic nuclei shape the evolution of entire galaxies. Even the ultimate explosion, the Big Bang itself, created the very framework of space and time within which all other processes unfold. In human experience, we often perceive destruction as purely negative, an ending without purpose. Yet the cosmos tells a different story. Here, endings become beginnings. Matter is neither created nor destroyed, but transformed, recycled through cycles of increasing complexity. A hydrogen atom formed in the first few minutes after the Big Bang might have existed in countless stars, traveled through interstellar clouds, become incorporated into a planet, and perhaps now forms part of a living organism contemplating the universe. This cosmic perspective does not diminish the violence of these events. A supernova obliterates a star that may have shone for millions of years. A gamma-ray burst releases more energy in seconds than our sun will produce in its entire lifetime. A black hole merger ripples the very fabric of space-time. These cataclysms operate on scales that dwarf human experience, with energies beyond our intuitive grasp. Yet, there is undeniable beauty in these cosmic fireworks. The expanding shells of supernova remnants captured by our telescopes display intricate structures of gas and dust illuminated by shockwaves. The jets from active galaxies stretch across millions of light years in graceful arcs. The cosmic microwave background, the afterglow of the Big Bang, shows subtle patterns that tell the story of our universe's birth. This beauty extends beyond the visual to the mathematical elegance of the physical laws that govern these processes. Einstein's general relativity describes how mass and energy curve space-time, creating the gravitational choreography of orbital decay and collision. Quantum mechanics explains how matter behaves under extreme conditions, enabling us to understand neutron stars and black holes. Thermodynamics traces the flow of energy from concentrated to diffuse forms, the arrow of time that gives cosmic history its direction. As conscious beings in this vast and violent cosmos, we occupy a unique position. We are, as astronomer Carl Sagan noted, a way for the universe to know itself. The atoms in our bodies were forged in cosmic explosions billions of years ago. The energy that powers our thoughts derives from the same fundamental forces that drive supernova and quasars. We are not separate from these cosmic processes, but integral parts of them, briefly assembled into complex forms capable of contemplating our own origins. Our very existence represents an improbable outcome of cosmic evolution, possible only because of the universe's capacity to recycle and reorganize matter through cycles of explosion and coalescence. In a cosmos that will eventually fade to darkness as stars exhaust their fuel and black holes evaporate, the current era of complexity and life represents a precious moment, a brief window when conscious beings can witness the universe in its prime. As we gaze at the night sky, we see not just points of light, but a history of creative destruction written in starlight. Each twinkling star represents a nuclear furnace that will someday exhaust its fuel. Many stars we observe are already gone, their light still traveling across vast distances to reach our eyes. Others are just being born in the turbulent aftermath of previous stellar deaths. In a universe so vast, even destruction is an act of creation. Every explosion, every flare, every collision gives rise to something new. Sleep now, knowing that even the wildest firestorms of the cosmos are part of its endless rhythm, and that in the silence after the storm, the stars still shine.